Hello, welcome back, everyone. We are in Chapter 18 in Fundamentals of Inorganic Glasses. Chapter 18 is all about the strength and toughness of glass. We are going to spend the next two lectures in this chapter. Today, we're going to cover some of the fundamentals of glass strength and toughness. And then next time, in Lecture 29, we will move on to methods for strengthening and toughening glass. So today, we're laying the foundation. And next time, we discuss methods for how to enhance the strength and toughness of glass products. So let's dive in with some typical strengths of glass products. Common glass products have practical strengths on the order of 14 to 70 megapascals. This compares to freshly drawn glass rods that haven't yet been handled significantly, that have somewhat higher strengths of 70 to 140 megapascals. Compare that to a braided glass rod. So take your freshly drawn glass rods, introduce some damage purposely, and the strength drops down to 14 to 35 megapascals. And if you introduce even more significant damage, say with wet scored glass rods, then the strength drops down to about 3 to 7 megapascals. On the other hand, if you go to armored glass has a much higher strength on the order of 350 to 500 megapascals. Compare that to handled glass fibers, a similar order of magnitude, 350 to 700 megapascals. But now look at freshly drawn glass fibers. So glass fibers right off the draw without touching anything can have strengths as high as about 2 gigapascals. And so there is an enormous variation in the observed strength of glass from as low as, say, 3 megapascals or even lower to as high as 2 gigapascals or even higher. So this is covering three orders of magnitude of practical strength values here in glass. Compare this to most metals that have strengths in the order of about 140 to 350 megapascals, falling somewhere in the middle. So what you can see is that glass is capable of being quite a bit stronger than most metals. But at the same time, most glass products that we use every day have strengths that are lower than most typical metals. So what is it that is governing the strength of glass, and how can we improve the strength? When we consider failure in glassy materials versus failure in metals, there are two other common observations that contrast the types of failure that are observed in metals versus glasses. First is that most metals neck or yield plastically before the actual failure occurs, whereas glasses do not show any ductility prior to failure. They just go immediately from an elastic response to failure. And what this means is that metals show what we call ductile failure, whereas glasses show brittle failure. So that is one of the key differences. Glasses are brittle versus metals being ductile. And whereas metal specimens prepared identically show a fairly narrow distribution of yield stress and ultimate fracture stresses, glass specimens produced apparently through identical means are likely to display a large variation in strength. And that large variation in strength is a byproduct of the brittle nature of glass, and as we shall see, a byproduct of the distribution of flaws that are present in glasses. Now, first, before we introduce flaws, let us consider the theoretical ideal strength of a perfect brittle material. And this is an estimate of that ideal strength that is due to Orowan. And Orowan's expression here shows the theoretical strength of a perfect brittle solid without flaws on the left-hand side. And he estimated that as being equal to the square root of this fraction here, which is the fracture surface energy multiplied by the Young's modulus divided by the atomic separation distance. And what Orowan was estimating here is basically how much stress would be required to break all of the bonds in a perfect, brittle, elastic, solid material, estimating the bond energies using the surface energy and the Young's modulus and the atomic separation distance. So if we put in typical values for a silicate glass, The fracture surface energy is on the order of 3.5 joules per meter squared. The Young's modulus on the order of 70 gigapascals, and an atomic separation distance on the order of 2 angstroms, or zero point 0.2 nanometers. And putting those values into this expression, you can see that the theoretical strength of a perfect brittle silicate glass would be about 35 gigapascals. This is an order of magnitude larger than even the observed strength of a freshly drawn optical fiber, which peaked at about 2 gigapascals. And so even a freshly drawn fiber is unable to even achieve 10% of what this theoretical strength would be of a perfect brittle solid. So what is going on here? Why is it that we are unable to attain this perfect ideal strength of a brittle material in real everyday glasses? And the reason is flaws. When glasses are exposed to the environment, they develop flaws especially in their surfaces. The flaws may also be in the bulk, and those flaws act to concentrate the stresses at the crack tip, and that leads to a compromised strength of the glass product. Now, the first person to deal with the effect of flaws on the strength of brittle materials was Inglis. And the Inglis criterion for stress at a crack tip considered that the practical strength of brittle materials is limited by flaws. So, practical materials are unable to achieve their ideal strength value because of the presence of flaws which locally concentrate the stresses. And Inglis considered an elliptically shaped flaw in the interior of the material that is, say, under applied tension. So here, for example, we have an elliptical flaw that has a height here of 2 times b and a width that would be 2 times c. So half the width here is this little c. And this is placed under an applied uniaxial tension, whereas sigma sub A is the applied tension. And this tension is not equally distributed because of the absence of any material here within the flaw itself. The stress actually gets concentrated at the flaw tips on either the left-hand side and the right-hand side of the flaw. And Inglis calculated this concentrated stress at the crack tip, which is equal to 2 times the applied stress times this geometric factor, which is the square root of c, this is half the width of that flaw, divided by rho, which is the radius of curvature. And the radius of curvature is calculated by b squared over c. So this is just a function of the geometry of the crack. So this is taking the applied stress, and then it is amplifying the applied stress using this factor, which depends only on the geometry of the crack. And what Inglis deduced is that when this concentrated stress reaches the ideal strength of the material, sigma sub m, from the previous expression due to Orowan, at that point, the specimen will fracture. And what this means is that the specimen will fracture at an applied stress, sigma sub A, that is significantly less than the ideal strength of sigma sub m because of the concentration of stresses that occur at the crack tip. And the concentration of stresses can be quite severe. So, for example, a flaw having a depth here, half width of 50 microns, could cause fracture at stress values as low as 35 megapascal. So it is a significant effect that lowers the practical strength of brittle materials compared to the ideal stress. Now, the more famous analysis, and the one that we use more often nowadays, is due to Griffith. And Griffith noted that most of the flaws in real materials are not actually occurring in the interior of the material, but are at the surface. And this is especially true with glasses because glasses are not made up of grains. They do not have grain boundaries. They do not have dislocations. They are not made by sintering, and so they do not have voids in them. And so it's much more likely for flaws to occur on the surfaces of glass compared to the interior of the glass, especially if there was good quality control during the glass manufacturing process to get rid of any gaseous or solid defects. And Griffith's analysis considered that flaws generally occur on a free surface and have a wide distribution of lengths, giving a wide distribution of severity in terms of their geometric ratio here of C over rho, the width of the crack divided by rho, this radius of curvature. And that Griffith also considered kind of this weakest link theory, where fracture occurs at the site of the most severe flaw, much like the case of the weakest link in a chain. So if you have a chain and you put a chain under tension, where is it that the chain fails? The strength of the chain is not given by the average strength of the links in the chain. The strength of the chain is given by whatever the weakest link is in that chain. And these flaws are called Griffith flaws. And Griffith's equation is shown up above here, where this sigma f, so this would be the stress at failure, is equal to this applied stress at failure, so sigma sub a, the applied stress at failure, and this is equal to basically a concentrated version of the ideal stress, where you've got 2 times the fracture surface tension here, gamma sub f, times the Young's modulus E, divided by pi times, and then the key term at the denominator here is C star, which is the critical crack length to induce fracture. And this expression is raised to the 1/2 power. And from Griffith's analysis, we know that although this surface fracture energy gamma sub f and the Young's modulus E depend on glass composition somewhat, they only vary by approximately up to 20% for most practical cases. And therefore, the factor here in Griffith's equation that is the most important factor governing the variation in strength is, in fact, C, this distribution of the flaw sizes. And this variation in C can be several orders of magnitude. You can have everything from atomically sized flaws all the way through flaws that are tens of microns or hundreds of microns. And therefore, what we can deduce from this is that the strength of glass is not intrinsic to its composition, but it depends greatly on the methods of processing, and it also depends greatly on the handling of glass after it is being made. Now, the next concept that we need to introduce is the stress intensity factor. The stress intensity factor is given by K, and it is defined as being the applied stress here, sigma sub A, times this geometric factor, which is the square root of pi times C. Where does this come from? This comes directly from Griffith's analysis here. So if you take this sigma sub A here, the applied stress, and now multiply both sides of this equation by the square root of pi times C, then what you'll get here in the numerator on one side of the equation is something that depends only on material properties, the square root of 2 gamma sub f times E. And then what you get on the other side of the equation is the stress intensity factor, which depends only on non-material related properties. So this depends on the applied stress and the length of the crack. Now, K, just by itself, is the stress intensity factor. What you will note is that the material will fail, the material will experience fracture when this stress intensity factor reaches the critical stress intensity factor. And we denote that by giving a subscript C to the stress intensity factor. So the critical stress intensity factor is K sub C. And this would be equal to now sigma sub f, which is the applied stress at failure, times the geometric factor related to the length of the crack, the square root of pi times C. And the units for critical stress intensity factor are the units of stress times the square root of length. And typically this is expressed as megapascals times the square root of meters. Now, when we consider the stress intensity factor, there are three different modes of fracture that are typically defined. They are listed here on the left and shown here, illustrated on the right. The first mode of fracture is the mode 1 fracture, which is the opening mode. You'll note here you've got a crack that is going from the side of the material, and then this is being placed into uniaxial tension, where the direction of that tension is orthogonal to the plane of the crack. So with mode 1 failure, this opening mode, the fracture plane, which in this case is the y-plane, and the direction of the propagation, which in this case is along the x direction, are perpendicular to the direction of the applied stress. And here, for mode 1 fracture, we denote mode 1 using a subscript Roman numeral 1, so it's a K sub 1. And so this would be the applied stress here along that direction, and then multiplied by the square root of pi times c. The next mode of fracture is mode 2 fracture. This is the sliding mode of fracture. And if we've got the same type of flaw geometry here, now the mode of fracture is due to shearing. And this shearing is sliding along the fracture plane over each other, as shown here. So mode 2, the sliding mode, is failure due to shearing, where the applied stress, which is sigma sub yx, acts to slide the fracture planes, the y-plane, over each other along the direction of propagation, along this x direction. And for mode 2, the sliding mode, we denote this as a K with a subscript Roman numeral 2. And finally, the third mode of fracture is the tearing mode. That is mode 3 fracture, and this is also a shear mode, except that the direction of fracture propagation is perpendicular to that of the stress on the y-plane. So you can see that this is a tearing mode, where now the shear is being applied along the perpendicular direction as to what it was in the mode 2 sliding mode. And for mode 3, the tearing mode, we denote that stress intensity factor as K with a subscript of the Roman numeral 3. So three modes of fracture lead to three stress intensity factors, K1, K2, K3. Now, note also from the previous slide that we have our critical stress intensity factor, which has a subscript with a little c. If you put these two things together, this should ring a bell of something in your mind, which is the fracture toughness of a material. And the fracture toughness is defined as being the critical stress intensity factor for mode 1 fracture. This is the fracture toughness. This combines the subscripts of mode 1 fracture, the subscript I, the Roman numeral 1, with the subscript of little c, denoting that it is the critical stress intensity factor. So we have K1C. K1C is commonly known as the fracture toughness, and the reason that it is K1C is that it is mode 1 fracture, and it is the critical stress intensity factor. And therefore, this fracture toughness here of the material would then be given by 2 times the gamma sub f times E raised to the 1/2 power. And a typical fracture toughness for a silicate glass is on the order of 0.7 megapascals times the square root of meters. The fracture toughness doesn't vary by a lot in most typical oxide glasses. And so if we want to consider toughening mechanisms, which we will do in the next lecture, we have to consider other ways to improve toughness beyond just compositional variations. So anyway, this is fracture toughness, and this is where it comes from. It is the critical stress intensity factor for mode 1 fracture. Now, another important topic in the strength of glass is static fatigue. With static fatigue, flaws apparently grow with time during the application of stress. So basically, if you hold a glassy material under a constant stress for given amounts of time, the flaws are growing during that time. And the growth velocity must be lower at lower stresses than at higher stresses, allowing for a longer delayed failure. And you can see this in the plot here on the right, which shows our stress here and the load duration. And what is being shown here is that the practical strength of the glass is lowering over time. So as you hold a constant load, as a function of time, the observed strength of that material is being lowered. This is due to a lengthening of the crack that appears over time under that stress. Now we observe another type of property called dynamic fatigue, which is kind of a variation on the same theme and has the same origin that I'll discuss in a moment. But this is now as a function of stressing rate rather than a function of stressing time. And what is observed with dynamic fatigue is that a faster stressing rate, so if you apply and release the stress on a much faster time scale compared to a slower time scale, this allows specimens to sustain higher stresses before failure. And here what we see is the average failure stress as a function of the stressing rate. And what is observed is that at higher stressing rates, the glass can withstand higher stresses before it fails. So again, this is bringing time into the equation here for determining the failure stress, where in both cases, if the stressing occurs at a shorter period of time, we observe higher practical strengths at shorter times and lower strengths at longer times. And so what is happening here is that this is related to the interaction of the glass with water molecules from the environment, where water, as we learned during our previous lecture on chemical durability, a water molecule can attack a bridging oxygen in a silicate glass, breaking that bond, forming hydroxyl groups, basically converting bridging oxygens into non-bridging oxygen. And every time a water molecule attacks a bond and breaks a bridging oxygen, that is equivalent to increasing that flaw by 1 atomic distance worth of length. And so if water comes into the crack tip, if you have, say, a crack here, and water molecules are being transported into the crack tip and reacting with that crack tip, which is under tensile stress, then that is going to lengthen the crack, and that immediately increases the amount of concentrated stresses at the crack tip because the crack just got longer. And so the explanation for both static fatigue and for dynamic fatigue is that over longer time periods, whether it's either a longer static amount of stress or a slower rate of the application of stress, the longer time period gives water more time to be transported to the crack tip, to react at that crack tip, and to lengthen the crack, which enhances the stress intensity factor until ultimately getting to failure. And we can see this on the chart here on the right, which shows 3 different regions for crack propagation velocity. So the y-axis here is the crack velocity in meters per second, shown on a logarithmic scale. And then the x-axis is the stress intensity factor for mode 1 application stress, so K sub 1. Now, the first region is region 1. Here at region 1, we have very slow crack velocities. This is slower than about 10 to the minus 7 meters per second. And here, what is observed is that the crack velocity increases exponentially with the applied load, as well as the relative humidity. And what we note here is that if we've got a higher applied load, that creates more tensile stress on the crack tip, which is basically pulling apart the bonds on the crack tip more and more. And what that means is that with a greater applied stress, the bonds at the crack tip are strained more, making it easier for water molecules to react with those strained bonds, breaking apart the bridging oxygen, and then increasing the length of that crack. Now, with region 2, what is observed is that there is a relatively flat velocity here with the applied stress, but it still depends upon relative humidity. So, and the different curves here are different relative humidities from a very dry condition shown here, and then going to wetter and wetter conditions all the way up through 100% relative humidity. And in each case, there is a flat region of the crack velocity, but that crack velocity is increasing by orders of magnitude with relative humidity. So in this region 2, what this is telling us is that if we've got a greater amount of humidity, there's more water molecules available to react at that crack tip. The kind of time that it takes for the molecule to react at the crack tip is no longer dependent on stress, but what is dependent is the number of water molecules that are available and basically how they can transport from the outside environment to the crack tip. And so in this region 2, we have enough stress that the bonds are being strained at the crack tip. And now the kinetics are basically being controlled by how fast we can transport water molecules from the humid environment to the crack tip, where they will then very quickly react and lengthen the crack. Now, in region 3, what we observe is that the velocity is independent of the humidity level, but depends exponentially on the applied load. The slope in region 3 is much steeper than in region 1. When we get to region 3, this is where we are basically crossing over into a failure region. So this is where we no longer need water molecules to react with the crack tip in order for the crack to propagate. It's already long enough that we have achieved the critical stress intensity factor, and then the crack is going to accelerate rapidly and proceed to failure. So the 3 different regions here are region 1, where the kinetics are controlled by the reaction rate between the water molecule and the bridging oxygen at the crack tip. Region 2, which is controlled by the transport of water molecules to the crack tip, and then region 3, where we no longer need the assistance of water molecules to lengthen the crack because the stress intensity factor is high enough to do that on its own. Now, these regions 1 and 2, where we haven't yet reached the critical stress intensity factor and where the velocity of the crack propagation is low, this is called the subcritical crack growth region. And what is observed here is that the cracks can grow very, very slowly until getting to the critical stress intensity factor, where the assistance of water molecules is no longer necessary. And we can use this to define what is called the static fatigue limit of the material. The static fatigue limit is the applied stress below which the crack does not measurably grow. And so if you could put your glassy material under static stress and you cannot measurably observe the growth of the crack, then you are still under the static fatigue limit. If you can observe crack growth, then you are above the static fatigue limit, which means that you need to worry about static fatigue, especially if the glass is being used in some sort of a load-bearing capacity. Now, this graph just shows what I described in words here about the slow crack growth by stress-assisted corrosion, where the high stress at the crack tip leads to a sharpening and a lengthening of the crack. And this is by water molecules that are transported to the crack tip and will react with those bonds that are under stress. So you've got the outside environment here, water molecules that are being transported to the crack tip. The bonds at the crack tip are strained because of the stress and the stress that gets concentrated at the crack tip. That makes it very easy for the water molecules to break apart that strained bond, converting the bridging oxygen to non-bridging oxygens that are passivated by these hydroxyl groups as shown here. And in that stage 1, we're basically limited by the reaction rate of the water molecule with the strained bond. And region 2, we're limited by the transport kinetics of getting the water molecules to the crack tip. And stage 3, the crack is already long enough that we're at the critical stress intensity factor. Um, Now, what happens after the glass breaks? After the glass breaks, we may want to figure out what was the origin of the fracture, what were the stressing conditions under which it was fractured, and fractographic analysis is an approach for studying the fracture surface. So if you take the broken piece of glass, look at it under an optical microscope or scanning electron microscope, you'll see images that look like this, where there's a lot of features on that fracture surface. And this can tell us a lot about the conditions under which the glass ultimately failed. Um, and there's a wonderful book about this by George Quinn, who is retired from NIST, and his book on fractography is freely available online. So if you Google it, you can download a copy, and it is an outstanding book with not only a great explanation of the basic science, but also a lot of wonderful images of different fracture surfaces. So this just shows an example of a fracture surface where we can see that the origin of the crack is shown here. And if you kind of follow these, if you look at the radial arcs here and go inward into their curvature, you can see where the fracture origin is. And this fracture origin is surrounded by a mirror region, which looks very smooth. And this is where the crack growth is initially slow. This mirror region ends going into a finely textured region known as the mist region. And as we go from the mirror into the mist, the crack velocity is accelerating and it is approaching its terminal velocity, which is governed by the speed of sound in the material. So that's going from the origin to the mirror to the mist region. Outside of the mist region, we have the hackle region. The hackle, you can see this is much coarser damage here. These are deeper radial ridges that surround the mist region as we have achieved our terminal velocity. And then you'll also see these Wallner lines outside, and these are produced by interactions between the fracture front and the stress waves, both of which are being limited in their velocities by the speed of sound and which are also reflecting off of the surfaces of the material and giving interactions as shown here. And those who are skilled in the art of fractography can use this information to show where the fracture originated. Was the fracture due to damage that was in the as produced material or due to damage that was introduced afterwards, and also estimate the stress that was on the material during fracture process. So there's a lot of information that you can garner from these fractographic surfaces. Next topic also relates back to the brittle nature of glass fracture. We noted at the beginning of the lecture that there's a wide variation of the observed fracture stresses, and this is due to the distribution of flaws and the fact that the strength of a given material is not governed by the average size of the flaw, it's governed by whatever the worst flaw is, whatever the longest, sharpest flaw is. That is what governs the practical strength of that particular specimen. And so there is a probability distribution called the Weibull distribution, which describes the probability of failure as a result of the distribution of single worst flaws in some ensemble of specimens. The Weibull distribution has the functional form shown here, where our probability is equal to 1 minus the exponential of minus sigma here, the applied stress, divided by some characteristic strength, sigma sub 0 raised to the power little m, where this exponent is called the Weibull modulus, and a larger Weibull modulus indicates a sharper distribution of stresses at failure. You can see that here on the left. This shows the probability density function of the Weibull distribution. So the probability of failure here as a function of the applied stress sigma. The broader curve here shows a lower Weibull modulus. This is a lower Weibull modulus of m equals 5. And if you just go to a higher Weibull modulus with the same characteristic strength, sigma sub 0 equals 50 megapascals, you can see how the distribution tightens up in going from m equals 5 to m equals 15. And this, the important thing to note here is that this is for the same characteristic strength of 50 megapascals, but what we actually care about is the lower tail of the distribution, because this lower tail tells us that there is some significant probability of having failure of a specimen at much lower stresses compared to the characteristic strength. And if you have a lower Weibull modulus, say this m equals 5, this tail of the distribution stretches out to much lower stresses compared to a higher Weibull modulus. And so where we really need to be concerned is this low tail, this low stress tail of the distribution, because we have to consider what is the strength where we can guarantee that at least, say, 99% or 99.99%, or whatever it is, that at least we've got a probability of surviving that amount of stress. And a lower Weibull modulus really compromises that low strength tail of the distribution. So in designing glasses, we want to have not only a higher characteristic strength, but also a higher Weibull modulus. So we can push the whole distribution over to the right, and we can also tighten up the distribution, make it more narrow to suppress this, this lower tail of the distribution. Now, if you take this graph on the left here and integrate it, you get the one in the middle, and that shows the cumulative failure probability, integrating from 0 up to whatever is on the x-axis here, the strength axis. And this gives us our cumulative failure probability. And you can see here for the lower Weibull modulus, the cumulative failure probability starts to rise at much lower values of strength. They pass through the same value, but then it's a much sharper rise here for the higher Young's modulus. And the other typical way of plotting a Weibull distribution is by taking the logarithm of 1 over 1 minus p. You take that logarithm twice, and then what happens is that linearizes this equation. And if you plot that versus the natural log of sigma, that converts this Weibull distribution into a line. And when you plot it in this way, you have a nice linear trend where the open circles here are your raw data. And then this gets fit to a straight line. And the slope of this line is m. And so the best way to get the Weibull modulus is to plot your data in this way to linearize the Weibull distribution. And then that gives you the Weibull modulus directly as the slope. And so a steeper slope here means a higher value of the Weibull modulus, which means a tighter distribution of the observed failure strengths, which is better. Last thing in this lecture are just some experimental strength measurement techniques. These are some typical methods that are used in glass research and in the glass industry. One of them is a 3-point bending test, where you have a bar of the material. It is supported at 2 points, and then is being pressed down on in the middle in a 3-point bending configuration. And then you should test at least 30 samples to get enough statistics, preferably 100 or more. You want to get enough statistics to be able to construct the Weibull distribution and to figure out the Weibull modulus. After the samples fail, then you can also go back and look at their fracture surfaces and do fractographic analyses to get more information on the details of how they failed. Another variation of the 3-point bending test is the 4-point bending test. It's very similar, except now you'll see it, not only is it supported on both sides, but the applied stress here in the middle is coming down with 2 points of contact instead of 1 point of contact. And what this means is that the shape of the applied stress is not triangular as in 3-point bending, where there's just a single maximum of stress here, but it is in fact trapezoidal, where the maximum stress is across a finite region here between these 2 points of contact here in the middle of the 4-point bending test. So this gives you a wider region where the stress is maximized in the center. Another test is the ring and ring test. In this case, the glass is supported by an outer ring, and then there's an applied stress with a smaller ring in the interior. And in this case, the stress is a constant across that full area of the inner ring. So this is another way to increase the fraction of the specimen that is under a constant maximum load under that testing. But in any of these cases, you need to make sure that you use at least 30 or preferably more samples to get good statistics here for constructing the Weibull distribution. The other test I want to mention is the ball drop test. This is where a stainless steel ball is dropped onto the glass sample, and then the height keeps increasing. This is not nearly as scientific, of course, but it is a common test used in industry, and so it is still used to assess basically how high can the ball be before it breaks. And another variation on that is what's called the device drop test. That's where you actually put the piece of glass into your device, how it's being used, such as a smartphone, and then drop the device from different heights and see how high it is before it breaks. The other thing I should mention is that any of these tests can be used either on as-made pieces of glass, like as drawn sheets of glass, for example, where the flaw distribution is just what came out of manufacturing, or you can do a braided test where first you expose the material to abrasion or damage under controlled conditions by sandblasting it, by hitting it against sandpaper. There are tumble tests where you could put the piece of glass into a container and tumble it using the contents that are found in, say, a typical purse, for example. All of these are ways of purposely introducing damage into the glass first, and then you would put it into these tests to see what are the failure strengths after the introduction of damage. So these tests can be done in either way. They both provide valuable pieces of information. So just be sure to know exactly what are the conditions under which the testing either is done or should be done for a given application. So, as I mentioned here, with other measurement considerations, you can measure the strength either as using as-formed glass or with abraded surfaces. Device drop tests, as I mentioned, are also commonly used to assess the performance of glass as part of a device. Fracture toughness itself is generally measured using samples with a known initial crack geometry, such as the chevron notch. This is where you put a known crack into the sample with a known geometry and then measure how much stress is required for it to break. And using that known geometry, you can get the fracture toughness. The other thing I should note is that under high stresses, cracks may branch, leading to fragmented crack patterns, and a little bit more on that in the next lecture. And as I mentioned, fracture parameters can be deduced from fractographic features. So that is your overview of glass strength and toughness. And next time, we're going to continue our journey in chapter 18 and talk about ways that we can strengthen and toughen glasses. All right, thanks everyone. If you have any questions, let me know, and I will see you next time.